Microsoft Fabric Data Science Deep Dive, how OneLake, notebooks, MLflow, AI functions, data agents, and Power BI create an end-to-end AI platform. Hello and welcome. Today we are going to take a complete deep dive into Microsoft Fabric Data Science, not as a single tool, but as a full enterprise data science ecosystem. Microsoft Fabric Data Science brings together data exploration, preparation, machine learning, model tracking, model scoring, generative AI, governed data access, semantic models, Power BI reporting, and AI-powered agents into one connected platform. The reason this matters is simple. Most organizations do not struggle because they lack data science tools. They struggle because their tools are scattered across storage systems, engineering platforms, notebooks, model registries, BI tools, security layers, and deployment pipelines. Fabric attempts to bring those pieces together so data teams can spend less time moving data and more time creating measurable business value. The starting point for understanding Fabric data science is the idea of unified analytics. In many companies, data scientists work in one environment, data engineers work in another, analysts build reports somewhere else, and business users consume insights in yet another system. This creates duplication, inconsistent definitions, unclear ownership, and slow handoffs. Fabric data science is designed to reduce that fragmentation by allowing data science workloads to operate directly on governed data in OneLake. That means data scientists can access curated datasets, shared data, experiment outputs, model predictions, and reporting-ready tables without repeatedly copying data between systems. OneLake is the foundation of this model. It acts as a unified data lake for Fabric, where lakehouses, warehouses, semantic models, shortcuts, and analytical workloads connect around a shared data layer. For data science, this is extremely important because model quality depends on reliable data. If a churn model, forecasting model, or fraud detection model is trained on a different version of the customer data than what the business sees in Power BI, the model may be technically correct but operationally confusing. OneLake helps reduce that gap by keeping data products, features, model outputs, and BI consumption closely aligned. The Fabric data science lifecycle begins with problem formulation. This is the stage where the team defines what decision the model should improve. For example, a business may want to predict which customers are likely to churn, forecast demand for the next quarter, detect abnormal equipment behavior, classify support tickets, summarize survey responses, or recommend next best actions. A strong Fabric project should not begin with a model. It should begin with a business question, a measurable outcome, a clear target variable, a known decision owner, and an understanding of how predictions will be used after they are generated. After the business problem is defined, the next step is data discovery. In Fabric, data scientists can work with lakehouses, warehouses, semantic models, files, tables, and shortcuts. This allows them to explore enterprise data without always needing a separate extraction process. A lakehouse can contain raw files, curated delta tables, and machine learning outputs. A warehouse can support SQL-based analytical modeling. A semantic model can expose business measures and definitions already used in Power BI. This gives data scientists several paths, depending on whether they need raw detail, engineered tables, business metrics, or reporting-aligned definitions. Data ingestion and orchestration are handled through Fabric's broader data integration capabilities. Data can come from Azure services, other cloud platforms, on-premises systems, business applications, files, and streaming or batch sources, depending on the architecture. For data science, ingestion is not only about loading data, it is about shaping data into a reliable analytical asset. A strong ingestion pattern should preserve lineage, maintain quality checks, organize data by domain, and make downstream training and scoring repeatable. Without this foundation, notebooks become fragile, models become difficult to reproduce, and business users lose confidence in the results. Once the data is available, data exploration becomes the bridge between raw data and useful modeling. Fabric notebooks allow data scientists to inspect distributions, identify missing values, detect outliers, compare groups, visualize relationships, and test assumptions. This is where teams discover whether the data actually supports the business question. For example, in a churn project, the team may examine customer age, geography, account activity, balance, number of products, and historical behavior. Exploration helps determine whether a model is likely to be useful, which features may matter most, and whether the target label is trustworthy. Data preparation is often the longest phase of the data science process, and Fabric supports it through notebooks, Spark, Python, Pandas, PySpark, and Data Wrangler. The key challenge is that real enterprise data is rarely clean. It can contain duplicates, null values, inconsistent categories, mixed data types, incomplete dates, skewed distributions, and irrelevant identifiers. Fabric notebooks allow technical users to clean and transform this data with code, while Data Wrangler provides a visual experience that can generate reusable Python code. This combination improves both development speed and reproducibility. Data Wrangler is especially valuable because it allows users to inspect and transform data interactively while still producing code that can be saved into a notebook. This matters because one-time visual cleaning is not enough for enterprise-grade data science. The same transformation steps must be repeatable when new data arrives. Data Wrangler can support actions such as dropping duplicates, handling missing values, removing irrelevant columns, encoding categorical variables, and preparing features for machine learning. The result is a workflow where users can move quickly during exploration while still preserving the logic required for production. Feature engineering is where domain knowledge becomes model input. In Fabric, features can be created using Pandas, PySpark, Spark SQL, Data Wrangler generated code, or reusable engineering pipelines. A data scientist might create ratios, time window aggregates, customer tenure calculations, behavioral flags, rolling averages, bin scores, or text-derived categories. Effective feature engineering is not about creating as many columns as possible. It is about converting raw business events into signals that help a model learn meaningful patterns. Fabric helps because feature creation can happen close to governed lakehouse data, and engineered features can be saved back into Delta tables for reuse across projects and teams. Fabric notebooks are the primary development surface for many data science workflows. They support code, markdown, visualization, Spark execution, lakehouse attachment, experiment tracking, and collaborative development. Data scientists can use notebooks for exploratory analysis, feature engineering, model training, evaluation, scoring, and documentation. Data engineers can use the same notebook experience for ingestion and transformation tasks. This shared environment helps reduce handoff friction because the same workspace can contain the data, notebook logic, experiment results, registered models, and final prediction tables. Apache Spark is essential for scale. Small datasets can often be handled with pandas, but enterprise data science frequently involves millions or even billions of rows. Spark enables distributed processing across clusters, making it possible to transform large datasets, engineer features, train certain classes of models, and perform batch scoring at scale. Fabric's managed Spark runtime reduces infrastructure overhead, so teams do not need to manually assemble every part of the compute environment. This is important because data science productivity depends not only on algorithms, but also on reliable compute resources, package management, and repeatable runtime behavior. Fabric also supports Python-based machine learning with familiar libraries such as scikit-learn, PyTorch, TensorFlow, XGBoost, LightGBM, and other ecosystem tools depending on the configured environment. This flexibility matters because different problems require different approaches. A classification problem may use logistic regression, random forest, or gradient boosting. A forecasting problem may use statistical models, machine learning models, or hybrid approaches. A text analysis workflow may use embeddings and large language models. Fabric does not force all teams into a single algorithmic pattern. Instead, it provides an integrated environment where teams can use familiar frameworks and tools.
MLflow integration is one of the most important capabilities within Fabric data science. In professional machine learning, training a model is not enough. Teams must know which parameters were used, what data was used, what metrics were produced, which artifacts were logged, which run generated the selected model, and how one version compares to another. Fabric's MLflow-based experiment tracking helps capture this information automatically. This transforms model development from isolated notebook code into a traceable and auditable engineering process.
Autologging makes experiment tracking easier by automatically capturing model parameters, metrics, datasets, and artifacts during training. Instead of forcing every user to manually record every detail, Fabric can capture key information as models are trained. This improves productivity and reduces the risk that an important experiment cannot be reproduced later. Teams can still customize logging when they need more detail, such as business metrics, custom thresholds, explainability artifacts, or project-specific tags. Model evaluation should go beyond accuracy alone. In Fabric, teams can compare models using metrics such as precision, recall, F1 score, raw GAUC, confusion matrices, loss, error rates, and business-specific KPIs. For example, in fraud detection, recall may matter more because missing fraudulent activity can be extremely costly. In customer retention scenarios, precision may matter more because outreach budgets are limited. In forecasting, understanding error distribution across product categories may be more valuable than relying on a single aggregate score. Fabric's experiment tracking helps teams compare runs consistently, but teams still need to choose evaluation metrics that align with real business decisions. Model registration gives trained models a managed identity. Instead of saving a model as a random file inside a notebook folder, teams can register models, create versions, compare versions, and connect them to scoring workflows. This is essential for collaboration because production teams need to know which model version is approved, which version is experimental, and which version should be used for inference. A registered model also becomes easier to integrate with batch scoring, real-time endpoints, monitoring systems, and lifecycle management processes. AutoML expands the platform for teams that want faster experimentation or need assistance selecting model families and hyperparameters. Fabric supports AutoML patterns through FLAM and related approaches, allowing users to test different algorithms and configurations with less manual tuning. AutoML does not eliminate the need for data science expertise. Instead, it helps accelerate baseline model creation, model comparison, and hyperparameter optimization. A responsible team still needs to validate data quality, leakage risk, fairness, interpretability, and business suitability before relying on the final model. SynapseML adds another layer of scale and capability. It extends Spark-based machine learning workflows and supports use cases such as text analytics, computer vision, anomaly detection, distributed inference, ONNX integration, and large-scale AI pipelines. This is valuable when teams need to apply machine learning across very large datasets or integrate models from different ecosystems. For example, a model trained in one framework can be converted to ONNX and executed at scale. SynapseML also supports explainability techniques such as SHAP and LIME, helping teams better understand why models generate specific predictions. Fabric supports multiple training approaches depending on the workload. Traditional machine learning can be implemented with scikit-learn or Spark ML. Deep learning workloads can use frameworks such as PyTorch or TensorFlow. Distributed machine learning and AI workflows can leverage SynapseML. Forecasting workloads can use time series libraries together with model tracking capabilities. Text and document workflows can use AI functions or large language model-powered pipelines. The key architectural idea is that Fabric brings these approaches closer to governed enterprise data and downstream reporting systems, helping organizations reduce fragmentation between experimentation, production, and business consumption. Batch scoring is one of the most common ways to operationalize machine learning. In batch scoring, a model is applied to a large data set on a scheduled basis or as part of a data pipeline. For example, every night a company may score customers for churn risk, accounts for credit risk, machines for failure probability, products for demand forecasting, or transactions for suspicious behavior. Fabric supports batch scoring through notebooks, Spark, and the predict function, allowing predictions to be generated at scale and written back to OneLake. The predict function is important because it standardizes how MLflow package models can be used for scoring. It supports batch predictions directly from notebooks or model item pages, and it works with several common model flavors when models are saved in MLflow format with model signatures. This reduces the gap between experimentation and operational use. Instead of manually recreating inference logic each time, teams can use a more consistent scoring approach that fits naturally into Fabric's model management experience. Real-time scoring addresses a different business requirement. Some decisions cannot wait for a nightly batch process. A web application may need to score a customer interaction immediately. A fraud detection system may need to evaluate a transaction while it is happening. A service workflow may need to prioritize a support case as soon as it is created. Fabric supports real-time prediction scenarios through model endpoint capabilities, allowing registered models to be exposed for on-demand scoring where supported. The decision between batch and real-time scoring should depend on latency requirements, cost considerations, transaction volume, governance needs, and operational reliability. After predictions are generated, the real business value appears when they are consumed. Fabric simplifies this process by allowing predictions to be written back into lakehouse tables and consumed through Power BI. With Direct Lake Mode, Power BI can access data directly from OneLake without unnecessary duplication or data movement. This is powerful because data scientists can produce prediction tables, while business users can immediately consume those predictions through dashboards, scorecards, and operational reports. The model output becomes part of the business decision environment rather than remaining isolated inside notebooks. Semantic link is one of the most important bridges between data science and business intelligence in Fabric. Business analysts often encode business logic into Power BI semantic models through measures, relationships, hierarchies, and domain-specific calculations. Data scientists frequently rebuild similar logic in Python or Spark, which can introduce inconsistency across teams. Semantic link through SemPy allows data scientists to connect directly to Power BI semantic models from Fabric notebooks. This helps teams reuse measures, understand business relationships, validate dependencies, and align analytical workflows with trusted business definitions. This connection between business intelligence and data science is critical because many model failures are not caused by algorithms. They are caused by inconsistent definitions. One team may define an active customer differently from another. One report may calculate revenue differently from a model training dataset. One department may exclude returns or cancellations while another includes them. Semantic link helps reduce these inconsistencies by allowing data scientists to work with the same semantic logic that business users already trust and rely on in Power BI. AI functions expand Fabric data science into generative AI-powered data enrichment. These functions allow users to classify text, summarize content, analyze sentiment, extract entities, generate embeddings, translate text, correct grammar, calculate semantic similarity, and generate custom responses. This matters because a large portion of enterprise data is unstructured. Support tickets, customer reviews, survey responses, maintenance notes, legal documents, emails, product descriptions, and call summaries all contain valuable signals. AI functions help convert that unstructured information into structured columns that can be analyzed, modeled, and reported on more effectively. Multimodal AI functions add even more capability by allowing workflows to process files such as images, PDFs, and text documents. This enables scenarios such as extracting fields from forms, summarizing PDF content, classifying uploaded files, or generating structured information from images. For data science teams, this can significantly reduce the manual effort required to transform documents into analytical datasets. However, AI-generated outputs should always be reviewed, evaluated, and monitored carefully because large language model-based transformations can produce errors, inconsistencies, or hallucinated results. Embeddings are especially important for modern AI applications. An embedding converts text into a numerical representation that captures semantic meaning. Once text is embedded, teams can perform similarity search, clustering, recommendation, semantic matching, retrieval workflows, and downstream machine learning tasks. In Fabric, embedding generation can become part of a broader data science pipeline. For example, a company could embed support tickets, group similar complaints, identify emerging product issues, and build dashboards that highlight recurring customer pain points and operational trends. Fabric data agents introduce a conversational layer over governed enterprise data. A data agent can answer natural language questions using selected sources such as lakehouses, warehouses, Power BI semantic models, KQL databases, ontologies, Microsoft Graph, and other supported sources. This allows business users to ask plain English questions without needing to write SQL, DAX, or KQL queries. For data science teams, this is important because it helps move insights beyond technical specialists and into day-to-day business decision-making processes. A Fabric data agent is not the same as a generic chatbot. It is configured around specific data sources, instructions, examples, permissions, and governance boundaries. It identifies relevant data sources, generates structured queries such as SQL, DAX, or KQL, validates those queries, executes them under the user's permissions, and returns human-readable answers. This makes it useful for governed conversational analytics, but it also means agents must be carefully designed, tested, and properly scoped. Data agent permissions are a major design consideration. Users must have access not only to the agent itself, but also to the underlying data sources the agent queries. For example, a user querying a Power BI semantic model through a Fabric data agent may only require read permission on the semantic model, while lakehouses, warehouses, KQL databases, and ontologies each have their own minimum access requirements. This least privilege approach is important because conversational access should never bypass existing enterprise data security controls. Governance is central to Fabric data science. Microsoft Purview policies, sensitivity labels, access controls, role-level security, column-level security, and tenant-level restrictions can all influence what users and agents are allowed to access. For data science teams, governance should not be treated as a final checklist completed at deployment time. It should be integrated into the workflow from data discovery through model deployment and operational use. This includes understanding which data is sensitive, who can access it, which features are appropriate for modeling, and how predictions should be interpreted and consumed. Responsible AI is equally important because data science systems influence real business decisions. A model may affect which customer receives a retention offer, which applicant is prioritized for review, which transaction is flagged as suspicious, or which machine receives maintenance first. Teams should evaluate risks related to bias, model drift, interpretability, data leakage, privacy, and operational impact. Fabric provides tools that support tracking, governance, and monitoring, but responsible AI still requires human oversight, documentation, validation, and clear business accountability. Monitoring is essential after deployment. A model that performs well during training can degrade in production because customer behavior changes, economic conditions shift, product offerings evolve, or source systems are modified. Fabric's monitoring capabilities help teams track experiment runs, Spark applications, model activity, and endpoint usage. Effective monitoring should include technical health, data freshness, prediction volume, model performance, latency, operational cost, and business outcomes. Without continuous monitoring, production AI systems can quickly become opaque black boxes that are difficult to trust or improve. Lifecycle management helps teams move from experimentation to enterprise operations. Fabric supports Git integration and deployment pipelines for selected artifacts, including machine learning experiment metadata and model metadata. This allows teams to separate development, test, and production environments more effectively. It also helps establish review processes, version control, release management, and traceability across the machine learning lifecycle. However, teams must understand what is and is not tracked. In current experiences, metadata may be versioned while experiment runs, and model artifacts remain stored within workspace environments. Environments and library management are another important part of production readiness. Data science projects depend heavily on package versions, runtime settings, Spark configurations, and custom libraries. A notebook that runs successfully today may fail later if dependencies change unexpectedly. Fabric environments help standardize libraries and Spark properties across workspaces and teams. This becomes especially important when organizations move from ad hoc notebooks into repeatable pipelines, scheduled jobs, and enterprise production workloads. Copilot in Fabric notebooks adds AI-assisted productivity for both data science and data engineering tasks. It can generate code, explain notebook logic, help clean data, suggest transformations, refactor code, optimize performance, and diagnose failures. This can significantly accelerate development, especially for repetitive tasks or unfamiliar syntax. However, Copilot should be treated as an assistant rather than an authority. Data scientists and engineers must still review generated code carefully, validate outputs, and ensure that suggestions align with business rules, governance requirements, and operational standards. Fabric documentation includes multiple examples that demonstrate how these capabilities work together in real-world scenarios. A churn prediction workflow is a common example. A company begins with customer, product, billing, support, usage, and renewal data stored in OneLake. Data engineers prepare reliable analytical tables within a lakehouse. A data scientist explores churn patterns in a notebook, uses data Wrangler for cleaning and transformation, creates features such as customer tenure and engagement scores, trains multiple models, tracks experiment runs with MLflow, registers the best performing model, scores customers with the predict function, writes predictions back to the lakehouse, and exposes insights through Power BI dashboards. Business users can then identify which customers are at risk and understand where proactive intervention may be required. A predictive maintenance workflow follows a similar pattern. Sensor data flows into OneLake from industrial equipment and operational systems. Engineers prepare time window features such as average vibration, temperature spikes, pressure changes, and operating hours. Data scientists train models to predict failure risk or estimate remaining useful life. Batch scoring identifies machines that require maintenance attention, while real-time scoring can support immediate operational alerts. Power BI dashboards help operations teams prioritize maintenance activities and allocate resources efficiently. The true value is not simply the existence of a model. The value comes from reduced downtime, safer operations, lower maintenance costs, and more effective planning across the business. A demand forecasting workflow highlights the importance of time series modeling. Historical sales, inventory levels, promotions, seasonality, holidays, pricing, regional demand patterns, and supply constraints can all be combined within Fabric. Data scientists can train forecasting models, track experiments, compare forecast accuracy, and publish forecasts into planning dashboards. Business users can then adjust inventory, staffing, procurement, and supply chain decisions based on those forecasts. Fabric helps because the same platform can store historical data, run modeling notebooks, manage experiments, and expose forecasts directly through Power BI. A text analytics workflow demonstrates where generative AI becomes especially valuable. A company may have thousands of customer comments, survey responses, product reviews, or support tickets containing important business insights. AI functions can classify each item by topic, detect sentiment, summarize long comments, extract product names, and generate embeddings for clustering and similarity analysis. Data scientists can then analyze trends, identify emerging issues, and combine text-derived features with structured customer data. This transforms qualitative feedback into measurable analytical signals that can support reporting, prediction, and decision-making. A governed data agent workflow shows how insights can become conversational and accessible to a broader audience. A company can configure a Fabric data agent over a lakehouse, warehouse, semantic model, and KQL database. The agent can be provided with instructions, example queries, business context, and a published description. Users can then ask questions such as which region has the highest predicted churn, which product category has declining demand, or which support issue is increasing the fastest. The agent responds within the permissions and governance policies applied to the underlying data sources, helping organizations balance accessibility with security and compliance. The role of Power BI in Fabric data science should not be underestimated. Many data science projects fail to create measurable impact because model outputs are not delivered into the tools and workflows where business users already operate. Power BI provides a natural consumption layer for predictions, model outputs, segmentation results, anomaly scores, and AI-enriched datasets. When prediction tables are stored in OneLake and exposed through direct lake mode, reporting can remain closely aligned with the latest analytical outputs without introducing unnecessary refresh complexity or data duplication. Security architecture should be planned early in any Fabric data science initiative. Teams need to define workspace access policies, lakehouse permissions, semantic model permissions, data agent permissions, endpoint access controls, and sensitivity labeling requirements. Organizations also need to decide who can create models, who can register models, who can deploy endpoints, who can publish data agents, and who can consume predictions and reports. In mature enterprise environments, these responsibilities are often distributed across data engineers, data scientists, platform administrators, security teams, compliance teams, and business stakeholders to maintain proper governance and operational control. Cost and capacity management are also important considerations. Data science workloads can consume significant compute resources, especially for Spark transformations, large-scale model training, batch scoring, AI functions, real-time endpoints, and repeated experimentation. Fabric capacity planning should account for workload patterns, concurrency, scheduled jobs, model endpoint usage, and generative AI consumption. Teams should continuously monitor capacity metrics, optimize notebooks, minimize unnecessary data movement, and carefully schedule resource-intensive workloads to control operational costs and maintain performance. One of the biggest mistakes organizations can make is treating Fabric data science as only a notebook environment. Notebooks are important, but the true value comes from the connected lifecycle. Data enters OneLake, is prepared in lakehouses or warehouses, explored in notebooks, tracked through MLflow, managed as registered models, scored through batch or real-time workflows, governed through Purview, consumed in Power BI, and accessed conversationally through data agents. That connected lifecycle is what transforms isolated experiments into scalable enterprise AI systems. The most effective implementation approach is to start small while designing for long-term scale. Organizations should begin with a single high-value business problem, identify the related decision process, prepare trusted data, build a baseline model, track experiments, publish predictions into Power BI, and measure adoption and business impact. The workflow can then mature by adding monitoring, automation, governance controls, model versioning, data quality checks, and lifecycle management practices. This helps avoid the common mistake of attempting to build a perfect enterprise AI platform before delivering any measurable business value. Microsoft Fabric Data Science is ultimately about shortening the distance between data and action. It provides data scientists with tools for modeling, engineers with tools for data preparation, analysts with tools for reporting, administrators with tools for governance, and business users with tools for insight consumption. When implemented effectively, it creates a shared environment where predictions are no longer isolated inside notebooks, but instead become integrated into operational business decision-making. The future of data science in Fabric will increasingly combine traditional machine learning, generative AI, semantic models, real-time intelligence, and AI agents. The role of the data scientist will also continue to evolve. Data scientists will still build models, but they will also design AI workflows, validate generative AI outputs, create governed features, evaluate AI agents, monitor production systems, and translate predictions into actionable business outcomes. Fabric supports this evolution by bringing many of these capabilities together into a unified platform experience. In conclusion, Microsoft Fabric Data Science is a comprehensive platform for building, tracking, deploying, governing, and consuming data science and AI solutions. It supports the full journey from problem definition to governed data, from notebooks to MLflow, from model registration to the predict function, from AI functions to data agents, and from prediction tables to Power BI dashboards. The opportunity for organizations is not simply to build more models. The real opportunity is to build a trusted intelligence system where data become predictions, predictions drive decisions, and decisions lead to measurable business outcomes. Thank you for taking the time to explore this topic with us.